Eat your poison. So it's a pleasure to have our next speaker, who is going to be a French person, and I enjoy that very much for obvious reasons. So Dominique Morvan works at Aix-Marseille University, and he's one of the early developers of the multi-phase approach that was described yesterday by Eric Müller, and he's going to tell us more about CFD modeling.
Okay, thank you for the introduction, and thanks a lot for the quality of the organization of this summer school and join with me. So, before presenting the application of CFD approach for file-point modeling, some recommendation concerning CFD. To be sure that you have some chance of success in the realization of simulation and also in the analysis of the results. The first one is to evaluate, because when we simulate something, we have to evaluate, even coarsely, the characteristic length and time of the problem. Also, don't use, it's difficult to translate le doigt mouillé in English. Perhaps arbitrary, yes. Don't use an arbitrary method to calibrate your mesh size. The mesh size must coming from physical phenomena which want to simulate. Simplify as possible the problem. We know that for wildfile modeling we need 3D, but for the problem 2D could be okay. Concerning also if how to manage the compressibility and the incompressibility of the floor. We have also to tackle many problems such as turbulence, combustion, radiation, eventually the interaction between combustion, radiation, and turbulence. Very important, use adapted numerical scheme, avoiding numerical dissipation, because if you use a very complex model of turbulence, a very bad numerical scheme, in fact, you you destroy. How do you do in developing this turbulence model? So to do that, you can use, for example, flux limiter strategy, divided scheme, ultra sharp, etc. There is a lot of resource study in the 19 and in the 18, which are to develop a good numerical scheme to do CFD. If possible, because wildfire is very complex problem, compare some numerical results with experimental data, and avoid the use of the following expression: our model is validated. Means that we have validated very partially, and we consider that now the model works well for every situation. And at last, consider that all models are wrong, but some ones are useful. There is a lot of physical phenomena governing wildfire, from the fire itself with the flame, the interaction between the atmospheric boundary layer with the vegetation, also how the vegetation degrades due to the heat transfer between the flame and itself. As we know, there is also turbulence, how to manage the turbulence. For the radiation, as indicated by previous speakers, the radiation in wildfire are mainly result from the soot production. And also, we can have also the problem at larger scale, how to manage to predict the trajectory of the plume, for example, to help operational people when we have a big fire somewhere, to help them, what is the air quality, what is the risk for the air traffic, etc. So wildfire is a multi-scale nonlinear problem. It is an example of the Los Alamos fire in May 2000. As we see that the plume dynamics can be characterized by length scale around, we can have a length scale for many hundred kilometers, which could be 1,000 and more. After, when we go near the fire, at different level, you reach, in fact, the ultimate level, which is the flame, the turbulent flame. And for hydrocarbon, turbulent flame can be evaluated as 400 micrometer. So you have a big difference of scale between these two problems. You have to choose. So the heat transfer, as previous say by other speakers, so the main heat transfer between the flame and the vegetation coming from two mechanisms, radiation and convection. Due to this heat transfer mechanisms, the vegetation dry, and then there is a chemical reaction at the solid state, which is pyrolysis, which transform the wood to gaseous, combustible and non-combustible gas, mainly CO and CO2, and also to char. And if there is if this combustible gas are located near earth sources, which is the flame, for example, we have ignition and then propagation. There is another mechanism for propagation, which fibrands, which could, in fact, develop the fires for a few kilometers. And we, as I said before, fibrands are the main source of vulnerability of houses located in the wildland-urban interface. Wi-Fi, some physical scales. So I can begin with atmospheric boundary layer interaction with the canopy. Many studies indicate that the large scale for the turbulence is more or less in the same order of magnitude of the depth, the height of the vegetation. In the atmosphere, the microscale range between 100 and 500 micrometer. So we have also another source of turbulence, which is due to the thermal plume, the dynamic of the thermal plume. Now, if we look at the interaction between the flame and the vegetation, so the combustion inside the fire is mainly turbulent, and the flame thickness, as I said before, is around 400 micrometer. Mainly due to for the radiation, so it's mainly coming from the soot. There is also convection, and if you look at you can evaluate, in fact, the length of penetration of the radiation heat waves in evaluating the extinction length scale LR, which can be ranged between 0.1 and 5 meters between shrubs and trees, for example. So the Wi-Fi modeling can be classified in three types. Statistical model, which is empirical. One of the more famous is the MacArthur model. Semi-empirical, like Rothermel, which is semi-empirical because there is a part of physics, because the Rothermel model can be viewed as energy balance inside the solid fuel layer, and with this parameter, which is evaluated empirically from experiments. And the last class of model, there is a lot of works are more or less physical, more or less which take into account more or less mechanism of heat transfer, which is the flame and the vegetation, from purely radiative and convective, etc. So this is a list of the different model which has been developed in the past. I have to explain now why it's interesting to do a CFD to study Wi-Fi. Empirical models are very good. Okay. Empirical model works well if you use it exactly in the same range of parameter that we have calibrate the model. So generally, it can be translated in a risk index. This risk index is a function of the air temperature and humidity, drought factor, wind speed, rain, and last rainfall, for example. Alors, if you look at the relationship, for example, between the rate of spread air and the wind speed, U, at a certain level, if you look at the literature, so you can summarize this relation as a power law function with an exponent b, which vary from 0.5 to 2. So, and there is impossibility to transport from one ecosystem to another one. So we have to develop, in fact, if you stay at this empirical level, we have to develop a relationship from each ecosystem. So it's very, very difficult. It's good if we have, in some places in the world, we have a very homogeneous ecosystem, like grassland, for example. But if you want to tackle a more complex ecosystem, like in Mediterranean region, it's more difficult. This is a relationship between the rate of spread and the wind speed, U. And we can see that this relation is mainly based, even for one, this is, for example, what we can find for a grassland. For low in this region, for low wind speed, we see that the rate of spread is relatively independent of the wind speed, with an exponent b, which can be larger than 1. Then, between two values u1 and u2 of the wind speed, we are more or less a linear relationship between the rate of spread and the velocity, which this region is very well known, especially during experimental flight, because it's a good condition to do experiments without risks. And when you increase a little bit above this value, you have a sort of saturation effect. And if you push the system very far, we can have extinction, like an explosion, for example. So the conclusion is that the constant, if you look at this relation, so with these two parameters, A and B, A is a function of the fuel moisture content, the slope, the leaf area density, and B could be also a function of the regime of propagation, which define, in fact, the interaction between the flame and the vegetation. So the semi-empirical model of the rothermal model. So this is so this is an example, very interesting example of the model I think it's even now it's the model which is the most used in the world. So I can skip because there is a lot of presentation of this model. This is an example of comparison between phytech. So this is a phi occurring in the region of Malibu in 1996. And this is a comparison of, so people of Los Alamos National Laboratory have compared numerical results between phytech and other tool. So in this situation, we have a configuration of canyon. So the emission in here, so the wind in here, there is in fact two mechanisms which can contribute to push to govern the phi behavior. The first one is the wind parallel to the canyon, and the second one is the slope which is perpendicular to the canyon. So this is a comparison of different approach. So the most physics is phytech here, and in phytech both slope and phi contribute to evaluate the local wind acting on the fire front. They have tested also the mesoscale atmospheric model introduced in PhyTech, which is IGRAD, and remove all the physics for the fire itself and replaced by the Rothermel model. And using that, in fact, the local wind acting on the fire front was due to the slope, because the fire, there is no retroaction of the fire on the wind. So we see that here, because this real fire are well documented, we know that it takes 10 minutes for the fire to go from the canyon to the top of the hill. So in this situation, in the configuration, PhyTech seems to be, works well. If you degrade a little bit the physics, it's in fact, even if you double the duration, but considering the complexity of the problem is not so bad. But with Farsight, so when there is no direct interaction between slope and fire on the local wind acting on the fire, you see that the prediction is not good. So this is it is for this reason that new model now try to the new generation of model coupled mesoscale atmospheric model with a model for the fire like PhyTech or Rothermel model or Balbi model, etc. So this is more or less the hierarchy of different wildfire model from semi-empirical flame map, for which the wind acting on the fire is the average wind conditions observed, and the fire is reduced to a fire line. The second level is proposed by, for example, the coupling an atmospheric boundary layer model, an atmospheric boundary layer model, such as WRF or Meso-NH, with a fire model, a local fire model, a model of propagation, like Behave or Rothermel or Balbi model, for example. So in this case, there is a retroaction of the floor to the fire. There is an action, in fact, of the slope, because when we calculated we calculate the atmospheric boundary layer, the flow was modified by the landscape. And the last one, the last class of model. So in the two first, the presence of the vegetation was not completely fully taken into account in the interaction between the floor and the vegetation. And the last series, when we can find FDS, Fireform, Vistar. So it's a full integration between the vegetation and the boundary layer. So we calculate effectively here what is the action of the presence of the vegetation with the airflow around. We calculate also, compare to the other one, here we have the fire line is only a source of heat injected inside the atmosphere. Why in FDS, Fireform, and Vistar we have a combustion model in the gas phase. And also, in the last class of model, we have a full interaction between the atmosphere and the fire. That means that the flow was modified by the slope, but also modified by the fire. And in the middle between the two classes of model, we have PhyTech. Why I class PhyTech in the middle? Because in PhyTech, in fact, we have not a real combustion model. In PhyTech, in fact, there is a calculation of the heat injected in the atmosphere from the degradation of the vegetation. But I have to say that, so these different level of complexity does not mean that we have to use a more complex model to study Wi-Fi. You have to fix the objective. And one objective, it could be also to develop simulation at large scale. And in this case, it's impossible to introduce too much detail in the simulation. How to simulate the behavior of Wi-Fi using a I think it's not complete, but yes, a detailed physical model. So from the physical phenomena, we have to tackle compressible flow, reactive flow, turbulent flow, radiation, solid gas interface, and solid fuel degradation. So with the scale, different scales, the wind speed, the flame thickness, the scale characterizing the turbulence, and also the extension length scale in the vegetation characterizing the radiation penetration of the radiation inside the vegetation. So in simulating Wi-Fi using a physical model, I propose for a long time to use a multi-phase approach. So the multi-phase approach, in fact, is structured in two problems. We have to solve two problems. One big problem inside the gas phase, with turbulence, combustion, energy balance, soot production and transport, and also radiation. And a second problem is describing the vegetation, how the vegetation was degraded by the flame. So we have to reproduce the drying, the pyrolysis, and combustion. Here, the combustion is the heterogeneous combustion at the surface of the solid fuel, the char. So we have interaction between the different block of model, and we use for the CFD. So we have to solve Navier-Stokes with low Mach number approximation. I will explain after why low Mach number is interesting for this kind of problem. And if everything works well, we expect to have a relatively good behavior of the phi. But you have also be conscious of the difficulty due to the mixing of the different phenomena, and these phenomena are characterized by a very non-linear behavior. Even when one non-linear problem is difficult, so if we mixed more, it's more and more difficult. So it's a reason also that we have some caution to use. Here I have also on this table I have classified or summarized the characteristic of four Wi-Fi model, Wi-Fi CFD model, Phi star, FDS, Phi tech, Phi foam, from different criteria. The first one is a criteria coming from the numerics. Phi star and Phi foam are, for the time integration, are implicit. FDS and Phi tech are explicit. So implicit needs more computational resource. And explicit is more easy to develop also, and generally it's more rapid. But the state of the art, we have also to say that the state of the art when you do CFD is to use implicit method. For example, Fluent, which is one of the most used CFD tool in mechanical engineering, we have not the possibility to push an explicit resolution. So it means something also. Concerning low Mach number, so we have a low Mach number approach for Phi star, FDS, Phi foam, not in the current version of Phi tech. It's also why in Phi tech they have to use also a relatively big mesh. Both are largely simulation for the turbulence. For the turbulence radiation interaction, which is, I can explain why it is important to take this model. We have in Phi star and Phi foam. In FDS, no, but there is a prescribed global radiant model. So in FDS, there is a calculation of the radiation, and if the objective of radiation does not reach a certain level in fact, they introduce a radiation ratio to be sure that the radiation transfer is sufficiently important for the simulation. And PhyTech is the same. Concerning the combustion model, so except PhyTech, all are introduced a combustion model. I can explain what kind of combustion models they have in this tool. All are multi-phase, not for the regular version of PhyForm, but there is some works done in PhyForm to introduce a multi-phase approach. Multi-phase approach means that for the regular version of PhyForm, in fact, the pyrolysis is only a surface pyrolysis, so it means that there is a model of heat transfer between the flame, the gas, and the solid fuel. And with a multi-phase, in fact, we simulate directly the degradation in volume of the fuel. For lab scale, so concerning the scale of use, we can use for lab experience for PhyStar, FDS, PhyForm. For PhyTech, not because mainly due to there have no low Mach number approximation. So the description of the fuel is relatively synthetic, reduced. We have few mesh to describe the fuel, and for lab experiments we need more. And for large scale, FDS, PhyTech, and FDS and PhyTech are very good for large scale simulation. For PhyForm and PhyStar, it's more difficult. We can have, but at relatively moderate large scale because of the detail we have introduced in this model. This is an example of a simulation done by PhyTech and FDS, reproducing a phi done in the international quant-phi modeling experiments. So here it's PhyTech. So what we have to say that even if you look something which seems to be flame, in fact it is not flame. It is the surface of temperature of the gas. Whereas for FDS we have really a calculation of flame in the gas phase. Alors, I have to explain why it's so important to introduce a low Mach number approximation. Alors, I take the example of a non-reacting flow, an ideal gas. So this is the continuity equation. Here's the momentum. And to close the problem, you have to introduce an equation of state. Here, it's the equation of state of ideal gas. And in fluid mechanics, we know that the relative variation of pressure due to the flow has an order of magnitude equal to the square of the Mach number. And with the Mach number is the ratio between the velocity of the flow and the sound of speed. So as an example, if we have a flow at 14 meters per second, we have a Mach number in air or 0.05, and so the relative variation of pressure is relatively small. So the question is that is it necessary to introduce in the equation of state this so small variation of pressure due to the flow? And we can decompose. This is a low Mach number approximation. So we can decompose the pressure in two contributions. The first one, P hat, which is an average pressure inside the domain. If the domain is fully open, this pressure could be can be a constant, which is atmospheric pressure, and neglecting in the question of state this contribution, the variation of pressure due to the flow. Alors, the advantage of this is concern mainly the time step. So most of numerical scheme have limitation to be sure that there is a convergence. Yeah. And this stability criteria is the CFL. So the CFL is a relation between the characteristic velocity v of the floor, but I explain why. What is a v after? Multiply by the time step and divide by the size of the mesh. We know that for explicit scheme, the limitation must be less than 1, and for implicit scheme, it could be larger than 1. Alors, for a full compressible floor, this v velocity must be the max between the flow velocity and the sound speed. So if we have a subsonic floor, it will be the sound speed. And in using the low Mach number approximation, the velocity v is reduced to the floor velocity. Alors, how to interpret, in fact, this limitation? In fact, so the velocity comes from the physics. The size of the mesh comes from the geometry, the constraint. So this criteria, in fact, act as a limitation of the time step. And it is very, very easy to understand that if we introduce a low Mach number approximation, we can reduce, theoretically, by a factor equal to 1 to Mach number from the situation if you do nothing. So it's quite interesting. Alors, we lose something. We lose, in fact, the propagation of the sound speed. We know that phi produce sound, but we can neglect as a first approximation. Concerning the turbulence, so the reference theory is Kolmogorov theory for homogeneous isotropic turbulence. So this represents, the main parameter for turbulence is the turbulence kinetic energy, and the turbulence kinetic energy is a function of the contribution. A turbulence flow must be viewed as a mix, a soup of vortices, and each vortices are its own contribution to the balance of to the energy, the turbulence kinetic energy. So this graph represents how the energy was distributed from a small wave number, means large scale, to large wave number, means small scale. So we can separate, in fact, three regions. This one, for large scale, when we produce the turbulence. The second one here, when the turbulence is dissipated by viscosity effect. And between the two, there is a cascade, means the degradation of the turbulence. So when we have a turbulence flow, we produce, but the turbulence is very unstable. And so there is normally there is a degradation, natural degradation of the turbulence. And after we have dissipation due to the viscosity. Alors, to simulate a turbulent flow, we have different approach. The first one is to do nothing, and which is direct numerical simulation, DNS. Do nothing means that we solve the Navier-Stokes equation without turbulence model. So it is used for relatively academic turbulent flow, also to study theoretically the turbulence. So it's interesting. It's done, but for Wi-Fi it's impossible. So the other approach is, in fact, to cut the problem in two parts. Simulate, calculate effectively partially some vortices, some structure. The name in turbulence is a structure. So calculate some structure, and so introducing, in fact, a filter inside the model. The size of the filter is the size of the mesh. We can't, with this approach, in fact, we can't reproduce vortices with a characteristic length larger than smaller than the mesh size. So in the other part, we have to introduce a subgrid modeling. And depending on the position, in fact, of this cut, more or less in this direction. Here, if you go here in this direction, we introduce a Rance model, Reynolds average Navier-Stokes equation, and if we have enough means in terms of computational resource, we can go on the right and try to simulate using a large eddy simulation. But we have to keep in mind that in every, so this is, so for a problem, so we see here it's a jet problem. We have to keep in mind that in using different model, we can't achieve exactly the same objective. DNS we have all, but it's expensive. LES we can have the main because we know that the large eddies contain more energy. But in Rance it's quasi impossible to find. There is a mix between. There is a situation from some model of Rance we can have some vortices, but not all. So to simulate a turbulent flow, so it's necessary to introduce a turbulence model. We have to keep in mind that a lot of turbulence models, the major one, are based on the concept of eddy viscosity. So associate to the idea that the turbulent structure are isotropic. And this assumption is only verified for small turbulent structure and not for large-scale turbulent structure. So it is, when we define, in fact, the cut, the mesh size, the ideal situation is that we must be sure that your cut is located here in the cascade. Because in the cascade, we know that the turbulent structure have a quite isotropic behavior. So I can skip this. This is an example of turbulence model, but I want to move. Yes. Okay. To move more in the Wi-Fi direction. So turbulence modeling, how to evaluate the turbulent integral length scale. It's not so easy because there is two sources of production of turbulence in a phi. The shear flow between the vegetation and the boundary layer flow. And the second one is the buoyancy between the hot gases and the plume and the ambient air. Donc, two mechanisms of turbulence. So therefore, these two mechanisms of turbulence can have its own turbulence length scale. Voilà. When I say turbulence length scale, is the integral turbulence length scale. Voilà. That means the scale at which we have more energy. So is this an example? Without the phi, the theory, when we look at the turbulence inside, for example, for a canopy atmospheric boundary layer interaction, the spectra function, the distribution of energy as a function of the wavelengths, wave number, is not exactly does not follow exactly the Kolmogorov theory, because with the presence of the vegetation, in fact, the vegetation acts at the system which broke the turbulence. It is for this reason we have this one. And due to the presence of vegetation, we have also a production of turbulence by wake effect. So you have to keep this. Alors, je vais voir un peu. Yes, okay. I can skip that. I will. So the first problem is how to reproduce the vegetation in a simulation. So if you have, so here it's a quite simple problem. I have written here an integral. So I've considered a tree with subject to the boundary layer flow, and around the tree I have construct a control volume, and this is this equation represents in fact the momentum balance between the inlet, the outlet, all the part. We're not on the ground because on the ground the normal velocity is 0. So here, here, and here. And here is a sum of external force. So in the external force, we have considered, I have not written, but the surface control, also the volume control exclude the tree. So the action of the tree was integrating inside these terms. Alors, how to evaluate now the action of the tree on the floor? Integrating the stress force along the interface air tree, impossible because of the nature of the fractal nature of this interface. So the solution is to perform a global balance and considering the tree, leaves, twigs, branches as a sparse porous media. And in this case, we introduce in the for example, here I have write a local momentum equation. So in this equation, compare with the steady state, etc. So in this equation here, this terms is a classical Navier-Stokes equation. I have just to introduce the effect of the force due to the tree, to the interaction between the tree and the atmosphere. So I introduce a force with a drag coefficient, and because the surface of the tree is very complex, it's impossible to calculate the projection like, for example, for simple geometry. If you do that around the cylinder or atmosphere, we can use as a reference surface the projection of this obstacle in the direction perpendicular to the flow. So for the surface, we introduce the surface of the interaction is introduced from this parameter, the leaf area density, which represents the ratio between the surface of in fact the effective surface inside a reference volume. So it is the surface divided by a volume. If you cut a volume of one meter cube of vegetation, and if you are able to calculate, to evaluate the surface of the vegetation, it is this ratio. So, as you see, the leaf area density is one of the parameters we need to evaluate to characterize the vegetation. So I reproduce this. So for the for example, for a problem of atmospheric boundary layer canopy interaction. So we have here, so these terms present just before, and this term is quite interesting. So this leaf area density, and if you integrate the leaf area density through the depth of the vegetation, we obtain, in fact, a non-dimensional parameter, which is leaf area index, which represents, in fact, a similitude parameter, which is very interesting if you want, for example, to simulate a boundary layer flow through a forest in a wind tunnel. Because the problem, if you want to simulate this real interaction for real forest, how you design the small tree is not only by a feeling. In fact, we have to, if you introduce this tree, we have to do our best to be sure that both the LIE, leaf area index here, for the real scale, are the same at the reduced scale. And in doing that, we can be relatively confident that the results we obtain for the experiments in the wood tunnel represent quite well the situation at the real scale. So, in the simulation, so we have to introduce additional term to represent the drag. But if you consider also the other equation of transport for the turbulence, we have also additional terms which is proportional to the drag force. Alors, how to evaluate now the drag coefficient? So there is some study, experimental study have been done, for example, for seagrass. I think the experiment was done in MIT. So this represents, in fact, the evolution of the drag coefficient as a function of a parameter, and this parameter is more or less the ratio of volume occupied by the vegetation, the volume fraction occupied, the volume fraction of the vegetation. And we can see, in fact, for this situation, there is two parts of the curve. If for here, in this part, we see that the drag coefficient is independent of so it's a part, this part is for very sparse porous media, and when the vegetation occupies a very small part of the volume. So in fact, there is not sufficiently interaction between one particle and the other particle, one structure and the other one, and we can assume that the drag is a function only of the Reynolds number. And on the other part here, so for more dense, here seagrass, but it could be a few layers. In fact, the CG, the drag coefficient, is a function of the volume fraction. So, and typical volume fraction for few layers range between 10 minus 3 and less to 10 minus 2. 10 minus 2 is for example, for liter. 10 minus 3 is for shrubs, and less if we consider the canopy of a forest. So we can have a typical value. I think, wait, yes, I have to skip this one, but yes. So when we have to solve a combustion problem, so we have to solve Navier-Stokes equation, and we have also to solve the species transport equation. Here, while alpha is a mass fraction of a chemical species. So the problem is here with omega point alpha, which represents the term of destruction and the production and destruction of this species by the chemical reaction. So we know that in phi, especially in phi at large scale, perhaps at the base of small phi, we can have a laminar combustion, but for phi at a certain scale, the main part of the phi is turbulence. So we have fluctuation of temperature, fluctuation of speed, many fluctuations. So the problem, in the phi we have to solve a turbulent flame, we have solid particle, we have chemical reaction, radiation, all are coupling, so very complex. As Arnaud said the first day, so to evaluate the rate of production destruction here, the rate of destruction of fuel, we have at local scale, we can use an Arrhenius law. And the question is, if you want to evaluate now an average value of reaction rate, can we use the same law, the same function, in replacing the mass fraction of fuel, the instantaneously mass fraction of fuel, mass fraction of oxygen, temperature, by their average value? The answer is no, because the level of fluctuation inside a turbulent flame, and means that the average fluctuation temperature by the ratio by the average temperature, it's much larger than 1. And I can here propose a very simple calculation. If you consider that locally in the flame, the temperature varied between two temperatures, T1 and T2. So in this case, the PDF of the temperature, the probability density function, is a sum of two Dirac distributions centered by T1 and T2, and it is quite simple in this case to calculate the value, the average value. And if you do that, we see that if you look at, for example, the pre-exponential factor K as a function of temperature, the ratio between the value we can calculate using the average temperature or in calculating directly the average value from the PDF, we see that this ratio is very far from 1. So it means that if you use the Arrhenius law in using the average value of temperature, etc., you do a lot of error. We introduce a lot of error in the model. So it is for this reason that when we have to solve a combustion turbulence problem, we have to also introduce a model for the turbulence combustion. Alors, to do that, we know that the interaction, we have to consider, in fact, the interaction between turbulence and combustion. Here it's a flame, so it's a premixed flame. And there is different regime of combustion. And this regime are piloted more or less by the ratio of size between the depth of the flame. So here we have the depth of the flame. And the depth, the size of the turbulent structure, which are in the neighborhoods of the flame front. So if the depth of the flame is so small that any turbulent structure can enter inside the flame, we are in the flamelet regimes. It means that the action of the turbulence is not only to wrinkle, the right name? Okay, to wrinkle the flame, but inside, if you want to calculate the the destruction rate of fuel, for example, we can use an Arrhenius law. The opposite situation is when a part of the turbulent structure can enter inside the flame. In this case, the turbulence has a real action of the fuel consumption terms, and we know that when we have a turbulence flow, if we increase the size of the flow, we increase the big structure, but we also decrease the small structure, because in fact, to destroy the production of turbulence coming from the large scale, we need smaller and smaller small structure to dissipate this energy. So there is not a translation. In fact, the spectra of the turbulence enlarge on the Bohr situation. So the large scale are larger and the small scale are smaller. So it is for this reason that it is quite easy to understand that when we have to treat a big fire, there is we can say that a part of the turbulence structure can enter inside and contribute to the mixing between the fuel and the oxidizer. So, to reproduce this mechanism, so it is the case, for example, in FDS, 5 star, I think in 5-4 also. One of the main turbulence combustion model used is the eddy dissipation concept type model. I explain, in fact, there is different variation of this model. So, in this case, if you look at the expression of the term of combustion rate, so finally we have to obtain a term with. It's important when you do a modelization to look up the units. So we have to obtain a term in kilogram per meter square per second. So here we know that if you have no fuel, if you have no oxygen, this rate must be 0. So it is for this reason that we introduce this term. And this term also permits, in fact, to reproduce the combustion when we are limited by the oxygen or limited by the fuel. And to introduce the time here, we divide this term by a time t, and the time t, in fact, must be reflect the mechanism of mixing. Here, the turbulence. So the time t must be calculated from the turbulence scale. I can check. Alors, 2h30. Alors, how describing a vegetation layer? So, when we look at a vegetation from the physical point of view, the main characteristics are the density, the volume fraction, the surface area to volume ratio, and the fuel moisture content. So on the field, we can use a different method to evaluate. Manually, it's very time consuming, but we can also use terrestrial LIDAR, for example. Alors, I can skip that. It's relatively. So, yes. So we know that the fuel classification is, yes, I can skip. So, je vais peut-être un peu. So, in model, in a multiphase model, so we have a set of equations to solve to calculate what is the state of the vegetation. So, the state of vegetation, there is an evolution between the original one. So first, the vegetation lost its water, then it dry, then it transferred to char and ashes. So if you assume that the vegetation stay fixed, no action due to the wind, we obtain, in fact, we can calculate the state of the vegetation in solving a set of ordinary differential equation. Perhaps I can, if I need some, yes. Okay. So we try to simulate a fire. If I follow what I said just at the beginning, so we have to construct a mesh. This mesh must be defined from two considerations. One, it must be less than the depth of the vegetation. Why? Because the depth of the vegetation is more or less the turbulence, the integral turbulence scale coming from the interaction between the atmospheric boundary layer and the vegetation. For example, when I say less, it should be 10 mesh through the depth of the vegetation. The second limitation is the extension length scale, which is very important also to verify. Donc, it is why I have defined this kind of limitation, this kind of law, to define my mesh in this region. After we can increase the size to be sure that the two mechanisms which is important in the simulation, the radiation, the penetration of the radiation wave inside the vegetation, and also the interaction of turbulence can be well represented. I think so too much equation. We have also to take into account, we can take into account of the interaction between radiation and turbulence. So it's modifying, this interaction modify a little bit the radiation transfer equation. So I can skip, yes, to show some application, yes. Boundary conditions. So the specificity of wildfire modeling is that we have a lot of open boundary conditions to manage, which is not so easy, very difficult. And especially we know that because the fire can generate its own wind, we have also, it's difficult to, we can't, for example, we can't stay here. Here, for example, I have imposed only a boundary layer profile. But if I maintain these conditions, it was impossible for the fire to have a retroaction on the flow. Because we fix the inlet flow, or the risk is that it takes the air from the top. So it's not good. Alors, to do that, in fact, at the entrance of the domain, and it is, we impose, in fact, so we have introduced an iterative process. We impose at the beginning a boundary layer profile, and after we imposed with a zero gradient for the pressure, and so we obtain. Alors, we have two things. In fact, at the top of the domain, we impose a velocity, because we consider that if the numerical domain is sufficiently high, the flame, the fire does not affect the boundary flow above, just at the entrance. So we know U top, which is a fixed value for the velocity, so wind velocity, and in the inlet region, we impose after pressure gradient, which evaluate like this. So we calculate. So within the process, we calculate the value of U star. We have U star here. So the results, we have U star here. After the calculation, we compare with U top, and we modify iteratively the pressure gradient imposed as the inlet. And when U star is equal to U top, okay, the problem is solved at the inlet. And what is interesting is that with this procedure, in fact, we are able to reproduce the action, the income flow and the inlet due to the interaction between the phi and the air flow at the entrance. Alors, some illustration. So it's quite old, but so this is an experiment done during a European project, Phi Star. This is a phi which was realized in Galicia, in the north of Spain. So the characteristic of the fuel, it is very dense, composed by mainly Ulex and other families. So to reproduce this fuel layer, we use in the model 14 solid fuel families. 14 because of different species and different also species which are, some are living and some are dead. The fuel depth is 1.25 meter, etc. And the slope 5 degree. So this is it's quite old because it is the first version of our model. It's a 2D version. Now we have a 3D version. But with this simulation, we see that what is interesting is that we are able to reproduce during the propagation of the phi, the recirculation of hot gases inside the vegetation. We contribute also to degrade by heat transfer mechanism the vegetation and therefore to contribute to the propagation of the phi. And for this experiment, for this configuration, we obtain quite good results comparing the rate of spread, even if we know the limitation due to the 2D simulation. Why performing 3D simulation? Because we know it is not costly, so we have to also to explain why. Because of the 3D structuration of the phi front, we have discussed about that before. This is on the left here. On the left here, yes. This is simulation performed in a grass at different value of the wind speed. The wind speed is fixed 10 meters above the ground, and we see that we are able to reproduce the structure in peak and valley of the phi front. We see also that this structure, the wavelengths change due to the level of the wind, and on the right we can see that effectively we can reproduce what can be observed experimentally, both here at small scale than here at large scale. The first simulation we have done in the 3D version of Phi Star is to reproduce the experiments performed in Australia by Cheney, Gould, and co-authors for a relatively small size of phi performed in grassland. Here it's the results we obtain for two values of the wind speed, 1 and 10 meters per second. What is interesting by this simulation, if you cut here, it's a cut of the numerical results. We see in color the temperature of the gas, and the line represents the direction of the flow. So we see that for 1 meter per second, there is an inflow on both sides of the phi front. It is a reason that we can say that this with a flame which is more or less vertical, and we can call this configuration as plume dominated. And on the other, for the other simulation, we see that the flow can cross through the valley, can cross the phi front. And so it's a reason we can say that this configuration at 10 meters per second is more wind driven. So we know from these experiments done by Chenet and Gould that the rate of spread is a function of the initial length of the initial line, W, with a stabilization of the rate of spread at around 150 meter or 200 meter. And if you want to, in fact, to study more basically, if you want to reproduce a quasi-infinite phi front, we can do that imposing on the two sides of the numerical domain periodic boundary conditions laterally, here, and here. So, and this is the result we obtain at 1 meter, 5 meter, and 10 meters per second. Alors, what we see is that what we see before, we see the structuration, the vertical structuration of the phi front in a peak and valley, but also we see the horizontal structuration of the phi front. Yes, and the combination between them, the two. Yeah, I can see. You can. So we see quite regular propagation. We see that in ingressing the wind speed, we also modify during the time the shape of the phi front, like this. We see the structuration is quite more complex. Okay, so this is we have seen. So we can perform some Fourier analysis to evaluate the wave number, for example, the structuration of the phi front. So this is an example of non-dimensional. So lambda is the wavelength of the phi front at the after Fourier analysis, and we have compared our results with the data obtained by Mark and his co-authors for the experiments down in the cardboard experiments. Alors, it is sure that it's impossible to use directly CFD approach to solve directly the problem at a real time. But I think we can use this kind of tool for the design, for example, of fuel brake. So this is a configuration. So we have here the fuel, the natural fuel, and between them we can define a zone which more or less we remove the fuel. Here for the calculation we remove completely the fuel. So we have used this kind of configuration. We have used the most simplified fuel we have in stock, grassland, because we have a lot of experiments concerning this fuel. So this is the configuration. And this is a top view of different results obtained at different value of the depth of the fuel brake, a range between 10 meters and 20 meters. So we have, for 10 meters, we see that the phi was able to cross the fuel brake. For 19 meters, we see that the phi cross, but cross marginally. And we can see the consequences on the phi intensity. And from 20, we can consider that, in fact, there is a small heating of the fuel on the other side of the opposite side of the fuel break, but the phi does not cross. So this is a view of the heat release rate for the all depths of the fuel. So we can see here, in fact, for 20, we see that the heat release rate decreases and decreases to 0 after a certain time. Here we see for 19 that compared to for 10, for 19 there is a decrease of the intensity, and after there is a stabilization at a relatively low level. So perhaps here there is something to do for the firefighter. So in defining the different level of if the different situation, the fire cross or not cross the fuel break, here we have evaluate for different value of the Biram convective number, because the Biram convective number is one of the non-dimensional number which can define separate between wind-driven and plume-dominated. The value of the effective, the more effective, the optimal value of the depth of the fuel break as a function of the height of the flame, or the function of the depth of the fuel. So, and we see, it's not surprising that, in fact, the optimal value for the fuel break must be done for low value of Biram convective number. It's meant for wind-driven, because wind-driven, the flame is more horizontal, and also it's more critical for the fuel break, for the efficiency of the fuel break. So, in conclusion, as a complementary approach to experimental fire, CFD modeling can contribute in the understanding of wildfire behavior. CFD wildfire modeling regroups various levels of description in order to reproduce fire at different scales, from scale less than 400 meters, like 5-star and 5-foam, for example, to larger than 1 kilometer for FITEC and FDS also. At a quite large scale, a simple coupling between an atmospheric mesoscale model with a simplified fire propagation model like Rothermel, Balbi, and the new model you produce, is sufficient to forecast the trajectory of the thermal plume associated to the development of wildfire, especially for the application to evaluate the air quality, to evaluate the exposure of people living not far from the, well, not far. It could be far, because if you look at in New York today, very far. Air quality, also some activity, like example for the airport activity, it's important. At a more local scale, a detailed CFD approach can contribute to the understanding of wildfire behavior, especially the effect of slope, wind, and other physical parameters upon the fire dynamics, the identification of regime of propagation, wind-driven, plume-dominated, slope-driven. As a post-fire or a fire safety analysis, CFD tools can contribute to understand some critical phenomena occurring during fighting operation, or help to the design of fire safety layout, such as fuel break. Conclusion 2, correctly define the objective of the numerical study. It's important. Don't forget the state of the art of the CFD modeling concerning the mesh design, the numerical scheme, the conversion monitoring, etc. Computational efficiency needs also by a great attention on physical model, low Mach number approximation, turbulence and combustion modeling, heat transfer modeling, boundary conditions, size of the computational domain, etc. Don't limit the analysis to few numerical results, explore the trends. As possible, comparing with experimental data. Don't forget that a model is not the full reality. Keep in mind the limitations. No model can be considered as validated. This qualification must be bound into all scientific reports. To generalize and compare numerical experimental results dimensional analysis can be a good option, BRAM convective number, fruit convective number, leaf area index, etc. And round trip between CFD models, phi models, and simplified physical models can be also very often useful. Thank you for your attention.
Thank you. We have time for questions.
Can I ask, since the fire type doesn't have the combustion model, so how do they analyze or estimate the flame height?
In fact, in FiTech, they calculate the amount of fuel, of solid fuel, which disappear during the propagation. And from this, they can evaluate the heat injected inside the atmosphere. So I think that the rate of spread, they evaluate the rate of spread from the temperature in the solid phase, for example.
But it's also a function of heat release rate, the fire intensity.
To evaluate. But I think the fire intensity can be evaluated from the amount of fuel, of solid fuel, disappearing inside the fire. Not directly from the rate of spread. In 5-star, in fact, to evaluate the fire intensity, because we have access to this data, we evaluate the fire intensity directly from the amount of fuel destroyed during the propagation of the fire.
So this was FireTech, right? And so the cell in FireTech is typically, I think, 2 meters.
Yes, 1 meter, 2 meter, yeah.
So
Mainly due to they have not introduced a low Mach number approximation, I think. And perhaps due to the fact also that they want to tackle large-scale problem also.
right. So
They do a good job, but our objective is more to large-scale problem.
yeah. So that's the point I wanted to make. So Dominique is right. It's a code that is going to study the interaction between a fire and the atmosphere at a scale that is typically several hundreds of meters.
Yeah.
And therefore, the small-scale physics associated with thermal degradation of vegetation and the combustion processes is not described. It's described by a simplified model in this big control volume that is 100 meters.
And for example, in FiTech, in fact, they consider that pyrolysis and burning occur inside one cell. There is no separation. There is no pyrolysis and after they burn above. No, it's all occur in the same cell. It is one of the hypotheses of the model.
Thank you.
Thank you. In this 5-star 3D plots, we saw that with line fire ignition,
Yeah.
you can capture this curved front
Yeah.
as opposed to the periodic boundary conditions. And you also talked about the U star and how you calculate it iteratively. My question was, can you capture this curved fire front if your domain width is
Alors, the first simulation I show with the parabolic simulation. So, the history of that. The first calculation we have done, we have simulated that the ignition was instantaneously on a line, and we obtain a curve fire front, but not parabolic. And after, to obtain parabolic, if in fact we reproduce the ignition procedure used by people which done the experiments, it means 2 people from the center with a torch go at the same velocity to the side of the fire. And doing that, we obtain a parabolic. Because in experiments, on the field, the ignition is not instantaneous everywhere.
And does the numerical domain matter?
Yes. The size of the domain affects the curvature of the fire front. Yes, it's right. Yes, that's right. I think, especially, for example, a study, Rodlin has shown this mechanism, the effect of the size. It is for this reason that to push our study more basically on the behavior of a quasi-infinite file front, we have introduced this also lateral periodic boundary conditions.
Question in the back first.
Thank you for the presentation. Following up on that question about the domain, you mentioned that for the input that you gave for the boundary condition for the velocity, you had to provide a feedback so that it was not being affected by the fire. Can you increase the domain size so that you have a region where your boundary condition is not being affected, rather than getting this feedback? I understand like it will be computationally expensive, but
yes, but in increasing the domain, the computational domain, you don't solve the problem, because the floor before the file is fully incompressible. So in increasing, if the file need more air in the process, if there is introduce an inflow, entrainment. Thank you. If the file entrain more air, this air must coming from somewhere. So if you fix even far a constant boundary, for example, boundary layer profile, we don't solve the problem.
I have another question. Like you spoke about the cascading. So the energy starts at the largest vertical structure, goes down to the column graph scale and dies down. Like in combustion, like the energy is being generated at the column-graph scale as well. That's where basically the perfect mixing is happening and combustion occurs. So it gives back the energy to the largest scale or the whole or the mean flow itself. Like how does it affect the?
Yes, it shows that in my explanation, I have presented the classical turbulence theory of Kolmogorov, which without considering the contribution to the buoyancy, etc. Yes. But it is. We know that it is one of the limitations. We have to, in fact, so we can evaluate a scale because the scale from the plume is not so easy to evaluate.
Yeah, there is a reverse cascade process due to buoyancy, especially buoyant instabilities, related or instability. So I think, to me, the picture of Kolmogorov is a little bit misleading for our buoyancy-loading flows. I don't think it ties very well.
Does it still follow the 5/3 law for does it violate that?
No, I don't think it applies. And if it also, I mean, it depends where you want to go with this. So for example, if you are looking at laboratory scale filers, and that's what you are trying to simulate, then the Reynolds numbers are usually small, and really this turbulent cascade theory viewpoint doesn't apply there. So there's a lot of misleading, I think, arguments in the literature on that. If you're going to the real scale problem, yes, you have a turbulent flow, but I don't think the Kolmogorov.
Yes, I have no time, but effectively, yes. If you have, for example, in the atmosphere, the effect of stratification with a plume, it is sure that we can. Well, there is different regimes, and the spectra is not similar. It's similar to. So we can have different. For example, effectively, in this configuration, we can have also a back, as Arnaud said, here in this part, we can have a reverse cascade. But in the atmosphere, normally, this reverse cascade occurs at relatively large scale. But with fire, it could be smaller.
I think we had a question there first.
Yeah, I have a follow-up question. So do you think because we are not able to capture this reverse cascade, we would never be able to have models that can actually accurately model convective boundary layers and capture the variations in the convective boundary layers. Do you think that that is the reason? Or is the reason that we are not capturing the radiation properly?
I think it depends the size of the file. Perhaps it is sure that if we have a very big file, like in Canada, for example, which affect a great part of the atmosphere, but we see that this reverse cascade, in fact, you see on this, if you have a reverse cascade, this reverse cascade does not occur from the Kolmogorov scale to the large scale. It come in between. So I think it's not a problem.
Well, if I can make a comment on this, it's this dynamic of buoyancy is part of the equations you're solving. So you are capturing correctly these effects at the level of the grid size that you have selected.
Yeah.
What you are missing is the smaller scale physics where it's already applied there. So there's some part of instabilities and mixing due to buoyancy at the subscale level that you won't get unless you are trying to put it in your model, and some people have proposed to do that in the literature, but it's typically not there in our current tools. But you are correctly getting that physics at the level of scales that are captured by your grid. I'm sorry we have to stop here. Let's thank Dominique.